Today I'm going to tell you about quantum mechanics, and I'm going to tell you about electrons. And I'm going to hopefully start nice and easy so that I can carry you through this 1 hour, telling you about not only the basics, but also sharing with you some of the questions at the frontier of this field. So I actually teach a class where I try to teach quantum mechanics to we call future leaders at Princeton. Used to be physics for poets. They rebranded it to more students. And I first part of my talk is actually, some people actually pay money to hear this, so hopefully it would be useful to you as well. But the idea is that, quantum mechanics, quantum theory, which I'll describe to you slowly, actually one of the most successful scientific theories around. And it's almost 100 years old. Next year is the 100th anniversary of quantum theory. And you may or may not realize that actually has made a modern way of life possible. And I'm going to go through some of the ideas that have underlied building technologies that has made HAM communicating with you and communicating online possible. It's actually still poorly understood. And it's not like those things where we say, oh, physicists don't really understand quantum mechanics. It's actually, there are possibilities in quantum mechanics in which we can discover new phenomena that after 100 years, which can have quite enormous impact, as I will try to share with you today. And actually, in one sentence, what is one of the special areas, which is actually what is one of the focuses of this week's workshop here at Aspen, the quantum mechanics of many particles. It's not just one electron. We're going to start with one electron or one atom. And actually, when you have many, many quantum particles, they create what we describe as quantum entangled states. I'll try to give you an example of what that is about. And I'm going to hopefully share with you that some of these things are bringing some new ideas in order to advance not just basic science, but new technology. The plan for the talk is to actually start from high school and talk about, what are the basic understanding of atoms, molecules, if you like, and tell you a little bit about materials and how we use quantum mechanics to understand materials. And as Natalia explained, what I specialize in is experimental physics, and my specialty is actually try to visualize electrons. Not with an optical microscope, with a kind of microscope I'll describe to you, actually uses quantum phenomena itself, actually visualize individual individual electrons. And what I want to share with you today is actually also some very recent work. This work that was just published, which actually breaks a puzzle that's been around, a search for like 90 years for a very special state of electrons when they are highly interactive with them. Okay, that's good? Okay, good. So let's get started. So, the premise is that quantum mechanics got started with us in the early 20th century in basically proposing that all matter is both particle and wave. And quantum properties can be described something called a wave function, which we're not going to spend a lot of time talking about what is a wave function, except to say this wave function tells us where the electrons are, where they are living. And, we can basically ask the question, what are they doing? Are they moving or are they stuck? And this wave function will tell us, for example, all of their properties. When you solve the equations of quantum mechanics on a computer, you find some truly weird behavior. Whereas, sometimes a quantum particle behave like a particle, like that bright spot in this picture. Sometimes it can just sort of seem like you can break apart and create something that looks like a wave-like pattern, as if water going through a sort of a constriction. And I'm going to show you images of this, how we image this actually using our instrument. Now, let's start very nice and easy. So electron was discovered before the turn of the 20th century in Cambridge, UK. It came before the discovery of quantum mechanics. It was discovered that atoms basically have electrons attached to them. Then later, it was the idea that the atoms will have a core that's a positive charge, and the electrons are bound to the atom. So, how do we understand an electron? How do we understand an atom? Here we are, not far from the music tent, and think about a string instrument, okay? And think about waves on a string instrument. And on a string instrument, those of you who play it know that basically you can think about a standing wave of basically the string instrument vibrating. And there's something called harmonics. And these are ways in which you can have different kinds of standing wave on a violin string. And actually, this analogy is a very good way to start thinking about electrons. If I gave you a box, I ask you, I'm going to put this electron inside this box. You say an electron is a particle, is also a wave. Electron can explore the box. It can move around this box. Actually, what it does when it moves around this box, just like you have vibration on a string, it just likes to live in a certain arrangements like you have on the string, where you would have these type of patterns, harmonics of motion of the string on a musical instrument. And this is the beginning of trying to understand. Of course, there are equations in which predicts this behavior, but you can just start with this analogy of thinking about how you have an electron like a particle and a wave. Now, if I put an electron inside a box, it will have these standing waves. Those wiggly lines you see in the left side, it goes positive and negative. Just like a string goes above and below where it would be straight. And the premise of quantum mechanics is it tells us is that once you know these wiggly lines, if you just basically look at where the wiggly line is not zero, that tells you where the electron is living. Okay? So far it's very simple, but actually the analogy with the string, you also have a notion which is these harmonics that we have on the string are basically analogous to what you hear the word quantum. When we say we have quantum mechanics, we talk about energy levels being quantized, we can use this analogy of thinking about these harmonics of a string as being kind of the frequencies in which the string can vibrate. In this case, relates to the energy at which the electrons can live in. Cannot live at any energy if the box is small enough, but they can live in this specific energy level. So we begin to see how we might ask the question what the electrons are doing at the single electron level when we think about these waves and if we can measure them, as I will show you in this talk, how we can do that. Now, let's take a step further. Let's put the electron inside the atom. We remember it has a positive charge, which is the proton, or it has some neutral particles there too. We're not going to talk about them. And you can think about this attracting the electron towards the nucleus, these positive charge of the proton. Again, it's just kind of like a particle in a box. Electrons like to be trapped near the proton. Okay, the box is not like the shape I showed you before. It has a different shape if you think about what the space electron likes to live in, but that's not really that important. But you can kind of understand an atom, electrons in the atom, in kind of very much the same way. The nucleus attracts the electron. Electrons are living in a box. They like to put up these waves. When you hear the word atomic orbitals, which you might have heard in your high school chemistry, if you remember, these are just standing waves, just like you will have on the string, in which it would tell you where the electron is living. Okay, the shapes can be somewhat complex, but the concept is actually kind of the same. And remember the quantized energy levels that we talked about when we talk about quantized harmonics on a string. Here, it carries over also to the atom. You can think about electrons living at very specific energies, living in specific patterns in these orbitals around the atom. Okay. And essentially, this concept carries you quite far. You think about each of these energy levels, it turns out that we're going to talk about what kind of particles electrons are in a moment, but it turns out electrons also have something called a spin. When you put electrons into these levels, you can put actually 2 spinning electrons in each of these levels. With that, guess what? You pretty much can understand periodic table. Okay? And so we've gone from sort of zero, thinking about just strings and boxes, and have come all the way to thinking about different elements, which has different protons, the nucleus, and different number of electrons. Now, my field concerns with not what electrons are doing inside atoms, it concerns with what electrons do when you put them together to create a crystal. And to me, you probably came to this talk and heard all these cosmologists talk about things in the universe as wonderful things that they study. And to me, every crystal is like it's its own universe, because the arrangement of atom in the crystal, as we'll describe to you today, create rules for electrons to move inside the crystal as if you're living in a slightly different universe in each different crystal. So, the diversity of phenomena you get in a crystal can be very different from each other, as we'll describe today. So you can think of this as a starting point of how to think about material. So we bring atoms together. There is attraction between the atoms to make bonds. We'll talk about the chemical bond in a moment. We kind of arrange them in a crystal. Let's just think of them as just a chain of atoms. Of course, what electrons are going to do is they're going to maybe hop one atom to the other. They exchange places with one another. That's a possibility. They can do that. What happens? So we started with these atoms and discrete levels of electrons in the atom. And basically, we had like a harmonics of the string. They have individual discrete energy levels. What happens if you put them inside crystal? Well, the electrons can hop around between the different sites. You can spend some time, if you like, at each site. If you know roughly that time, if you wish, you can basically show that, no longer electrons have a specific energy. Actually, when you put them in a crystal, they can have a range of energy. Those range of energy inherent, they start with the range of energies they started in an atom, but the kind of the range of energy is associated with how long it takes them to go from one atom to the next. Okay? There's something called the uncertainty principle you might have heard about, position and time, position and momentum and being kind of uncertain, Heisenberg. Turns out there's another uncertainty principle between energy and time that actually gives you the width of the range of energies electrons can have in these things we call bands. Why am I telling you all this? With this, now you can understand essentially most of the materials around you. What do I mean? Well, you can understand what is a metal, something that conducts electricity. Because in a metal, electrons move from one part to the other, can change their energy. In order to change their energy in this diagram, there have to be some, electrons fill up. You have so many electrons in the material. And if they fill up to the last energy level, and if they move around, they will change their energy. If there are no levels available, can't move. That gives you the metal. Okay. Also, you can understand what is an insulator. Because if you filled out all these levels, and you basically end up with like a big, what we call a gap to get to the next level. And that level is very far away. Basically, what I mean by far away is like, in our scale of, you have something in the real world, you have something that's at some temperature. If that energy range is sort of small or large compared to the temperature, electrons can't get across, so you have yourself an insulator. You'll say, okay, that's pretty boring. Why are we talking about this? Well, this is the basis of almost all the technology that we have. Okay? All the technology we have there's one thing more, a magnet, which I'll get to in a second, which is a metal which conducts electricity between your transistors. I'll talk about the transistor in a moment. As your hard insulator, which is diamond. Okay? It doesn't conduct electricity at all. And you have yourself silicon, which is conduct electricity not well. That's actually good, because then you can try to control how electricity moves through silicon, and that gives you basically transistor.